Hey everyone, I'm Kishan, I'm lead engineer at Presidio. So in this video, we're going to see different stages involved in LLM training. And so this video is going to be a shorter version and a condensed version of Andrei Karpathy's 3-hour long video on LLM training. So we are going to see how LLM trainings and what basically happens when you give something like this, So what can you do? So what this text is about, so what's happening behind the scenes. So there are a lot of things getting generated for just a short query that you have asked. So what these texts are about. So the first step in training your LLM is downloading and processing the internet data. So there's this company called Hugging Face where they have curated a data set of internet and they have published it as a data set called FineWeb. So this data contains about 15 trillion tokens, and it occupies a disk space of 44 TB, and it involves various stages to come up with this data set. So the first step is filtering, URL filtering. So basically you don't want your LLM to contain all the data from the internet. So there are few data that you want to blocklist or few URLs that you want to blocklist. So there is this website where it has like a list of websites that needs to be blocklisted. So probably like fake news, gambling, malware sites, phishing sites, adult content. So these data are something that you don't want your LLM to be trained. Okay, so once you have this filtering, and the next step is text extraction. So this FineWeb, they are using a tool called Common Crawl. So this is nothing but a web crawler tool. So web crawler works on HTML, so it does not see your data as is in the website. So it sees the data like what you are seeing here as a HTML. So these tags, and you don't want these to be a part of your training data, because these are going to add noise to your training models. So you have to remove these things. So that's what this step is about, extracting the text from the website. And the next step is language filtering. So this step decides what languages your model is going to be well known of. Okay, so if you consider this FineWeb, so they have a filter where they filter around web pages with 65 more than 65% of English content. So that means this data set only focuses on the English content. So if you use this data set in your model, then your models may not be answer questions that's based on Spanish or French. Okay, so these are the main core stages in downloading and extracting the data from the internet. So there are other layers on top of it, like filtering the quality of the data, deduplicating it, and you have your own custom filters, and personally identifiable information removal, like phone numbers and address. So these are some of the additional layers that you can add on top of your filtering process. So once you have everything in place, so I think these guys have published it publicly, the same data set that I was talking about. So this one, show it to you. Yep. So you can see these are the textual data that they have extracted from the internet, and this is the URL, the date of this website. So all these data are publicly available. So companies like OpenAI and Anthropic, they are going to have something similar for all their LLM models training data. So not exactly this, they have their own process of extracting the data. So once you have all this data in your data set, so the next step is feeding to the LLM, right? So we cannot, this is just one example I have taken from that from the web page. So this one, yep, this web page. So I have just extracted the text, and this is how it looks like, and this is how your dataset is going to look like when you feed it to the LLM. So we cannot feed this entire text as it is to the LLM. So we need to find a way to represent this data before we feed it to our neural network models, because the way neural network works is, so it requires a sequence of symbols to be passed as input. So we need a way to represent this in a symbols, And one naive way would be, converting this data or this sequence of text in a binary, like zeros and ones. So this could be one way where you could represent the data, but you can see this is huge. So this is really huge than the actual original content, textual content. So from this one, you need to figure out a way to shorten this sequence, but still you want to represent that same content. So one way you could do is, so you just take first 8 bits from this data, and then you convert it to a bytes. So 8 bits to a bytes. So in that case, you would land up something like this, right? So you now see the data or the length of this sequence getting reduced, because we have more symbols to represent, but we have shorter sequence. So you have to repeat this process until you get more symbols and shorter sequences. So, or there's one more way, is like you search for a pair of sequence from this number. So here this sequence is getting located in multiple places, so you combine it with a new symbol. So similarly, you take any random pair of symbols, and you do this similarly and recursively until you can shorten the sequence of this representation with a lot more symbols. So this process of converting the text to a sequence of symbols is known as tokenization. So each organization have their own tokenization models. So this one is from GPT-4o model. So if you could just paste, so this is one website where you could visualize the tokenization process. So if you could just paste the entire text, you can scroll down and see how they are getting represented as symbols, or we call it as tokens. So each individual symbols here are nothing but tokens. So you can see, so the same data here, it has much shorter length of sequence. So with this way, we can easily feed this into a neural network, and the process is going to be pretty simple, rather than just dumping the entire binary data or the bytes data, which is huge. Okay. And yeah, so there are like these are like unique symbols, and so I think GPT-4o has around 100k unique symbols of these. With those 100k unique symbols, they could represent the entire data in the internet. Now that we have this data, so the next step is to take this data and train your neural network model. So the way neural network works is it expects a sequence of one-dimensional input, and it's going to predict the next output. So for that, you take any random sequence, probably this first 4 tokens, or any sequence of tokens from this data set, and you're going to feed it to the neural network model. So it might look something like this. So so here the context window that I have taken is 4. So it could be anything like 8,000 or 16,000. So for the simplicity, I have taken this 4 tokens. So each token represents the text, so the performance of her. So you feed this sequence of tokens into your neural network. So we are going to see how this neural network is going to look like, but the output is going to be the probability of the next token. So here, as I said, so OpenAI has this 100,000 unique tokens. So in that case, it's going to be come up with a probability for each unique tokens in that data set, right? So it could be like for this specific use case, so here the direction has 3% probability, case has 1%, and this large has 2%. But if you see in the dataset that we have, basically not the entire dataset, but the snippet of the dataset that we have. So the next token is 4410, which is, I think, large. Yeah. So large one. So now that we know 4410 is the correct token, so we have this mathematical way of updating our neural network so that the probability of the correct answer is going to be high, right? So the next time when you do this update, so the probability of this might become like 4%. This goes down to 2% or something, or whatever. So that the next time when it sees this pattern, the performance of the sequence of this pattern, it is going to come up with a higher probability for this token, because it has been trained, or we have uh, tuned this neural network such that it needs to come up with the correct answer next time. So you are not just going to do this for this 4 token, so you are going to do this for all the sequence of tokens parallelly for a different window, right? So this is going to be happening for the entire data set, so this is going to be happening parallelly, and this is going to take a lot of time. So to give you a quick example how that neural network looks like, so this is more like a mathematical expression of the neural network, and we have just assumed 4 token again here, but it could be anywhere from 1 to example 8000, or nowadays models like Gemini supports even 2 million tokens, right? So just think about that. And these parameters are nothing but weights, and this is what we would be updating whenever we found the correct answer to be, or whenever we want to increase the probability of the correct answer. So initially this weight would be initialized with the random values. So whenever you update your neural network, this weight is going to be adjusted or tuned such that the probability of the correct answer is going to be high, right? So here we are seeing that we have 12 weights, right? W12. So weights, when I say weights, it's nothing but the parameters. So even if you see the open models like a Llama or a Mistral, so they when they release a model, so they come up with these 8 billion, 12 billion, some label number, right? So this billion values are nothing but the parameters. So their model has 8 billion parameters or 12 billion parameters. So now think about this mathematical expression for those kind of large volumes, right? So 2 million tokens with 400 billion parameters. So you can imagine how long this neural network is going to be, right? And this is going to be processed for each sequence in the entire data set. So that's why this training process is always a time consuming and very cost consuming as well. So this is a very costlier process in the entire training phases, and this actually takes around 4 to 6 months depending upon the data you have and then the context length you decide to train on. But this is not going to happen very often, this process. So they just do it once, and then they take this as a base model and they refine it for the upcoming fine tuning the base models, right? So this is how the mathematical expression is, and to visualize how the neural network is. So this is nano GPT architecture, this is a transformer architecture, and this is what revolutionized the Gen AI, the LLMs performance, right? So I honestly don't know what happens in this instance entirely, but this is how the architecture looks like. So you see the input here, right? Let me just zoom in. So this is the input that you're going to feed it to the neural network, and finally you will get the output. So your input will be passed through all these layers to decide the next tokens or predict the next tokens, right? So this will be like a prediction of the outputs, right? So yep. So this is nano GPT, and so this is GPT-2 small, this is GPT-2 XL, and this is the GPT-3. So this might look like that 4-dimensional world in the Interstellar movie, but this is actually the GPT-3 which got released in 2020, and this is when OpenAI and the ChatGPT becomes very popular. Okay. All right. So now we have trained our model. So this is just an analogy that we use. Like you think it of as a DJ system where you tune the knobs so that you get a better output. So you tune the bass, the volume, the stereo to get the better output, right? Initially it's gonna have all the noises, but as and when you tune this, you get a better output. So you're going to stick to that setting whenever you play a next song or whatever. So now that we have seen the internals of the neural network and how it predicts the next token, so there's this important stage called inference. So in this stage, we are going to generate new data based on uh, what it has learned from the patterns in the parameter that we have set after the training. So this process is pretty straightforward. You take a single token and you feed it to the neural network and let it predict the next token. Okay, so in this sequence, we have taken one token from our training data 976 and it has predicted 6198, which is exactly the next token in our sequence. And now this output is getting added to the previous input for the next step or for the next iteration, and that is being fed to the neural network again, and it predicts 328, which is exactly what we have in the training set, and you are going to repeat the same. So but here you can see, so this time it has predicted 13659, which is not true, right? So in our training data it's 4410. So this is fine because it's actually it's more like a prediction. It's not going to follow everything that we have in the training data. Probably if you just read it out, so this is the performance of and this token is nothing but a student. So the performance of a student, this sentence actually makes sense. Probably it might have seen more of these sequences in the training data apart from this sequence that we have in our example, right? So this is how the inference work, and this is how we work with LLMs. So if you see, I think Andrea Karpathy has tried to simulate the training of GPT-2 architecture. So this is just a few logs that he had in his training stage. So these steps are nothing but individual steps, or updating our neural network with more with the refined parameters such that it produces good output, right? So this is what we have discussed. And so after each, probably like after 20 steps or 30 steps, so he's printing or he's performing this inference just to see how the model is generating the new content, right? So this is after 540 steps out of this 32k, and if you read it aloud, this still makes sense, but it's not the sentence formation, the vocabulary, it's not properly constructed. But this is still a early step. Probably by the end you reach this 32k, you might have a better construction of words and the vocabulary. So this is how it works. And so you might be wondering, like, if this is just about prediction of next token, so how useful this model is going to be. Because if you check this example, so we are using a base model called Llama 3.1, which is a 405 billion parameter. And if you are asking a question like what is 2 plus 2, it is not calculating or it's not answering anything from this answer. You can see it's just about trying to complete that question, right? So it's just predicting. So this what is 2 plus 2 is being converted to sequence of tokens and it's given to the neural network, and it's about predicting the next token. It's not actually calculating it, right? So in this case, we cannot use this base model, but there are definitely few use cases where you could make use of this base models. Like, so instead of asking a question, you can start something like this. Here is my top 10 list of landmarks to see in the Paris. So it tries to complete this sentence, but this patterns it might have seen more in the internet data, so you most probably get the correct answer here. So just for example, if you copy any data from the Wikipedia, right? So if you paste it here, it's going to give exactly the same content whatever it's being followed after we copied, right? That means it has seen this pattern, this exact pattern in this in its training model. So it's trying to repeat the upcoming or the prediction of the next set of sentences. So there is a new interesting use case here, right? So if you see, so this pattern, so English and an alternate translation in Korean. So if you are giving something like this as an input and you stop at a word called teacher in English, so it is going to give you that alternate translation of teacher in Korean, right? So this is called as in context learning. So what happens is, so when you feed it to the LLM or a neural network, so it is going to understand the pattern from the context you have given, right? And it's trying to give you the same pattern in the output. So you can see it's trying to come up with a new pattern here, morning. And if you again feed it to the input next time, it is going to come up with a translation of morning with Korean translation, right? So this is what we call in context learning. So there are definitely use cases where you could use this base model, but from a real world perspective, it's not going to be that much useful. So now that we have our base model, which is nothing but internet document simulator, right? So you might be wondering, how can we especially make this kind of situations work? So you ask a question and you want your LLM to answer your question as an assistant, right? So we are going to take this base model and we are going to fine tune on top of the base model such that it can answer you as an assistant. So the first step, the first stage is training. Now we are going to moving to the post training stage, which is one of the post training stages is supervised fine tuning. So in this supervised fine tuning, you are going to swap the internet data with the data set of conversations. So the data set might roughly look something like this. So you have a set of conversations, a human or a user with assistant, a set of questions and answers, right? So now you're going to feed this data to your LLM and you're going to update that weights so that it's going to learn pattern from these conversations, as well as it's going to maintain the vocabulary and the sentence formation that it has learned in the training stage. Okay. So this one again, so when we are not going to give this data set as it is, we are going to convert them into tokens. If you see here, okay, so here again I'm using this tick tokenizer visualizer, which is usually easier to visualize these conversations as well. So as you can see here, we are constructing a delimiter for each conversations. So this is like the start of the turn, and this is the separator. I mean, after this separator, it's going to be the actual content of that conversation, and this is the end of the turn. And so we kind of have these delimiters for each conversations. And if you see this kind of tokens, so this is like relatively new, which has not been in the training set. So this pattern LLM might not have seen in the training set. So with this, LLM can understand whenever it sees this token, it's going to assume like this is a start of some conversation, and this is the whose turn it's going to be, and this is the separator, and after that this is the content, what is 2 plus 2, and this is the end of the conversation. And this is how so we construct these conversations, and we add kind of delimiter so that LLM can understand so the start and end of each turns, and we are going to feed it to our LLM neural network. So we are going to follow the same process as we have followed in the training stage. So you feed these conversations to your neural network, and you are going to update your parameters until it gets trained. Okay. So you are not going to reset these parameters. So you're just going to stick to the same parameter, but you're swapping the training data with this data set of conversations. Okay. And so there are so you might be wondering, like, who's going to curate these data set of conversations. So it is going to be a human process. I mean, initially it used to be a human process. Now it's been automated with the help of LLMs. So you can see this is the articles or the research paper from OpenAI on training language models to follow the instructions with human feedback. So in this paper they have said, like, they used around 40 contractors to collect these set of questions and answers and feed to, so that it can be fed to the neural network, right? So this is more like a human effort at the initial stage. And so there are like certain guidelines as well. So this is a few examples of how the questions should be constructed, and so they do have like a guidelines on how it needs to be, you know, the question and answer should look like. So it should be like helpful, truthful, and harmless. So whenever, as a human, whenever you try to come up with these conversations, so you have to follow these things. So now this, it's all like automated with the help of LLMs. Okay, so this, with this you can actually feed it to the LLM, and so by the end of this supervised fine tuning process, your LLM can actually answer your questions. So if you go to Hugging Face and check any open models, right, open source models or like Llama, so you should be seeing, let me check the space. Yep, models. So you see there is this label called instruct. So this is nothing but a base model which has been supervised or supervising fine-tuned with the instructions. So if you see a label with base, that is not being supervised. So it's going to complete the sentence, but it's not going to answer your questions. But any model that's tagged with this label instruct, it's going to answer your questions. And most of the LLMs are going to have these, any open source LLM are going to have these instruct, because they're not going to release the base model which doesn't have much use case. So this actually concludes the process of fine-tuning with instructions. So when you ask a question in ChatGPT, like what is 2 plus 2, so just think of it as interacting with ChatGPT in the interface. So you ask this question, so ChatGPT is going to construct this delimiter. So they're just going to wrap this pattern of delimiters around your query, and they're going to send it to the assistant like this. So this is what it's being fed to the LLM, and LLM is going to come up with the answer like 2 plus 2 is 4, and ChatGPT is going to again construct. So when you ask the next question, ChatGPT is again going to do the same thing, and it's going to construct all these delimiters around your query, so that it can mimic what it has seen in the training data, the same pattern what it has seen in the training data during the supervised fine tuning. So this is how so we make our LLM model act as an assistant, so that it can answer our queries, right? So we have seen two major stages in the training. So the first one is pre-training and the training, where you collect the data and you feed it to the LLM, and this makes LLM learn the patterns and the vocabulary in the internet. It's basically a lossy compressed version of the internet, and that's what you get as a base model, and it's going to be a internet document simulator. But you don't want to simulate the internet, you want it to answer certain questions, right? So for that you have to do this post training process, where you just swap the internet data and feed it with the conversation data sets. So with this, LLM can understand the pattern of answering a question like how a human would do. So with this, your LLM can answer all the questions that you ask. So basically the conversation turn patterns, right? So now there is this major step of post training called reinforcement learning. So this process is going to be, if you take any companies like OpenAI, so they will have a dedicated team for this stage, pre-training stage, where they collect the data and feed it to the LLM, and they will have a dedicated team to construct this data set of conversations. And so this takes around, as I said, 6 months, and this might take around it is going to take relatively less amount of time, probably like a day or two. It depends on the data set that you have. And so this is where you want your LLM to come up with your solution. This is where you actually test if you have built the right solution or not. And again, you're going to give a feedback to your model such that it can learn from the human patterns, right? So just consider this analogy, how you would learn, and how so you learn content from a textbook, right? So that you can be an expert in any domain, right? So So now consider this book. It has three major sections: the actual chapter content, which is the exposition or the background knowledge, and the worked out problems, basically a sample, a problem and a solution, which it's been attached in the chapter itself, and a practice problem. So you have a problem, but you don't have the solution, but you'll have a final answer at the back of your book, or as a separate answer key, right? So this exposition or background training knowledge is what we have seen in the initial stage of LLM, which is getting the data and training our LLM with the exposition. And the worked out problems are nothing but the simulated conversations between human and the assistant. So basically the question and the answer. And the third step is what we are trying to do with the LLM. So we want to simulate this section of practice problems, where so you have a problem statement and you know the answer, but you want your LLM to come up with the intermediate steps and solutions, such that it gets to the final answer, right? So for that, so we have to do this post training called reinforcement learning. So you take a problem statement and you're going to let your LLM come up with multiple different solutions, and you're going to pick the best ones, and you're going to feed that back to the LLM, such that it gets updated. Again, the same way getting updated to produce the better results, right? So in this example, we have a logical question, and it came up with around 15 answers. So we are picking the top solution and trying it, and we are going to repeat it for multiple problem statements, right? So these are like verifiable domains. So because this is a mathematical problem, so it has a definite answer, right? And probably a coding problem would have the same thing. So you don't need a human to validate these answers. You could just have a program written in your code which could do all these validations. So for problem statements like coding, you can have test cases to see which solution passes all the test cases, right? So you can take that solution and give it as a feedback to the LLM, right? But there are certain domains where you cannot have automated way to validate it, right? So just consider this query: write a joke about pelicans, or you could have a query like write a haiku poem about pelicans. So these things needs human validation. So humans are going to validate the output of these solutions. They are going to pick the right one, because so humans are better at comparing the solutions rather than coming up something from scratch, right? So they can take the best solutions and they can fit it to the LLM. So this process was actually a human heavy process, but now it has been simplified with introduction of another neural network, where so that neural network gets trained with the pattern of how human would answer these questions, or how human would select these solutions out of the different solutions. So that gets trained with another LLM, and this LLM we call it as a reward model. So now this reward model is going to be in place, and it's going to validate and pick the correct solution, or pick the best solution from the different set of solutions, and we are going to feed it back to the LLM. And so we don't have to automate completely. So there will be human process in the middle to validate if this is going right or not. So with this, like the entire reinforcement learning makes your model work on a problem that it has never seen better. Okay. So this actually concludes the training stages of LLM. So you have three main stages, as we seen: the pre-training and training, and the post-training. So in post-training, we are going to have a supervised fine-tune process, where you have a definite question and answer, so that model can understand how to answer it as an assistant. And you're going to have a reinforcement learning for a problem that it has never seen. So with this, I think you would have like some idea on how this content is now getting generated, right, for a question that you have asked. So this is how the LLM works behind the scenes. I hope you like this video. So thanks for watching. Bye.